Hi, welcome back to the Shiko Math Practice Lab, Learning Through Practicing. And we are in the topic of optimization. This is our practice set number 2 for the optimization problems. And so for the previous video, we work on the 5 problems for the level 1 optimization problems. And so level 2 problems are a little harder than the level 1, but it's not too bad. It's just, your objective function sometimes a little bit more complicated than the level 1 problems here. Okay, so let's take a look. Those are the 4 problems we're going to practice. So the first 2 problems is like if you give me the 2 different curves in the plane, how do I find the minima or maxima distance between those things, between these 2 curves? Or the other 2 problems we're going to talk about is instead of like the rectangle, we're going to talk about box, and we try to maximum minimize the volumes or the maximum minimize the material we use. So those are the 2 problems we're going to work on. Okay, so now let's go ahead and let's start to, start to work our problems here. Okay, now let's take a look at our first ones here, all right? So for the first problems here, we said, what is the maximum vertical distance between the line y equal to the x plus 2 and the parabola y is equal to the x squared? Okay, when we try to do this type of the problem, the first things here, let's probably will be easier. Just let's try to graph it, right? So this is okay, so this is the graph here. So y is equal to x plus 2, so it's the 2 here. So this will be our, so this is y equal to the x plus 2 here. Okay, now for y equal to x squared, so y equal to x squared, it will be something like this, right? So, okay, so the y equal to, okay, so something like that, right? Okay, so this is this curve here, this is y equal to the x squares here. So I want to find the vertical distance between these two. So I want to find the maxima. Okay, so that means from here to here, right? So the vertical distance, that means I want to find this distance, right? This is what we call it the vertical distance. And what I want to do here, I want to find the maximum value of this vertical distance here. Okay, so now let's try to start like we did before. So first things here, let's try to find our objective function. Okay, so objective function is the distance, right? So here is the distance here between these 2 curves. So this is a distance here. So this is y equal to the x plus 2, and this one is y equal to the x squared. So the distance will be from here to here, right? So it will just be x plus 2 minus x squared, correct? And I want to find the domain is from -1 to 2. Okay, so this is the objectives here. And now in here, because in here, this is what is our subject to, right? So x has to be between 1, the 2 and the -1s here. Okay, so now let's take a look. How do I do that? So this is d prime here, or maybe I should write this. So, okay, so instead of put it over here, so in here I only have 1 variables here, right? So this is objective function. So what is our conditions here? So conditions here, we say I want to find the x is between -1 and 2 here. Okay, so now that's the same way. Here is already is just a function of x, so I don't really need to do anything. So I just take the derivative of the distance. So this is 1 minus what? 1 minus 2x here, right? So I will set this one equal to 0. Then I will solve for x equal to what? X equal to 1/2 here. And then since we are subject to the x is between -1 and 2 here, right? So basically I want to find, because this is maximum, I want to find the absolute max. So let's see here. So so this is our critical value. So this is 1/2, right? So if you choose something less than 1/2 here. Let's see what is less than 1/2. If it's 0, so this is a positive, right? So I have increasing. If it's greater than, it's negative, so I have a decreasing. So now we confirm, that this one will give me what? This one will give me the maximum value. The local max could happen here. But because my function is restricted to -1 and 2, so let's take a look. How do I find the maximum, the absolute max? So now I put the two endpoints, right? So when x equal to 1, what is what is my distance here? The x equal to -1 here, right? So it's -1 plus 2 minus 1, right? So what do you have here? You have zeros here. It's kind of like it makes sense here, right? So let's you have zeros here. Now I have x equal to 2 here. So when x equal to 2, then the distance will just be 2 plus 2 minus 4. This one is 0, so it's here, this point. That makes sense also. So now when the x is equal to 1/2, then the distance here will be the 1/2 plus 2 minus what? Minus 1/4 here. So what I get here is 9/4, right? Because this is local max, but it's in the closed interval. So I also know this is absolute max here, right? So I know the absolute max distance is what? Is equal to the 9/4 here. Okay, so this is a little bit different type of the problems than the level 1 problems here, right? Because then your condition is like they give you the domains here. Your condition is a little bit different than what you need to do, replace one with the other, like we did for the level 1 type of the problem. Okay, so now let's take a look at our next problems here. So the next problem is what is the minimum vertical distance between the parabolas here? Okay, so now let's just like we did before. So maybe it's easier. Let's try to take a look here. Let's try to graph it. Y equal to the x squared plus 1. So it will be some curve like this, right? So this is y equal to the x squared plus 1. Okay, now then the y equal to the x minus x squared is probably will have some parabola like this, right? So this is y is equal to the x minus what? X minus x squared here. Okay, so now let's take a look here. So what do they want to find? They want to find the distance between these two curves as well. But now in here, what I want to do? I want to minimize the vertical distance. Right? Okay, so now let's try to write here. So my objective functions, what is my objective functions here? It's the distance between these two. So it's the distance again. So the distance here, this is x squared plus 1 and what? X squared plus 1 minus x minus x squared. right? Okay, so if you want to simplify it a little bit, use the distributive property, get rid of the parenthesis, you will have this is 2x squared minus x plus 1. Okay, now what is the condition? In here, we don't really have any conditions, right? So the x here really is to all the real numbers here, all the real numbers to see which one will give me the shortest distance here, all right? So now I want to find the minimum value here, so I will say d prime. So the d prime here is 4x minus 1, okay? So the 4x minus 1, this is what? This is zeros here. All right, and then what is the x here? X is 1/4 here. Okay, so the x equal to 1/4, so I put 1/4 here. So this is a d prime. So for anything less than 1/4, this is negative, right? If negative, that means my function is what is decreasing. All right, then everything greater than 1/4. So if you put 1 here, this is positive. That means it's increasing. And so for these numbers here, I know this will be what? Because your function, because you have, this is a polynomials, right? So this is a polynomial. It's decreasing, and then it's increasing, right? So it's a go something like here. This is a polynomial. It's a go decreasing, then it's increasing. So I know this one's here, this is the local mean, but also is what? This is also is absolute means here. It's because it's right in here, right? Okay, so now see, let's see what is the vertical distance here. So when x equal to 4, so the distance will be what? Will be 2 times 1/4 square minus 1/4 plus what? So plus 1 over plus 1. That's right. So if you do that, you will get the minimum distance is 7/8. And it happened at what? X equal to 1/4 here. All right. So this is the second type of the problem. Let's be very careful, right? So we don't really have a subjective function. It's just to tell you what is the domain of the x. That's the differences between the level 1 problems we did and this ones here. Okay, let's take a look at the number 3s here. The number 3 is they tell you a box with a square base and the open top. Okay, and this box have a volume of the 32,000 centimeter cube. Find the dimension of the box. That will minimize the amount of the material we use. Okay, so like we did before, the easiest, is always going to help, right? So if you do a graph here, so this is a box, and I have a square on the bottom. So let's see, the length here is B and B is here. Then the height of this box here, let's say, is H. Okay, and now what do we want to do here? We want to find the material it's used, right? So let's see here, be careful. This is our objective function. So of our objective function, because I want to find the minimum material used, right? So it's really the surface area, right? So how many surface here? We have 4 sides, right? Each one is a rectangle, like in here. This is a rectangle. What is the area? Is B times H, right? How many? 4 B times H, correct? So it will be 4B times H plus the bottom, right? So this box is open top, but I have a bottom. So what is the bottom square? Is B square. Okay, so be very careful, right? Because this is the open top here. And now this one, back to similar, the level 1 problem, then we're going to have another condition. So this condition is the volume is 32,000. So I know the volume here is 32,000. So what is the volume? Is base times height, right? So it's b squared times what? Times h here. Okay, now this back to what we had before. So we need to replace one variable to be a function of the other variable. So here I said, maybe h is easier because I don't want to take the square roots. So I would say the h is the 32,000 over b squared. Right? Then what you do here, after you drag, you substitute back to your objective function. So the surface area will be b squared. Okay, so b squared plus 4 times b times what? Times h. So what is h? Is 32,000 b squared. All right. So here you can cancel of the 1b, and maybe it will be simplified when you take the derivative. Okay, so now the SA, I'm taking the derivative here. So what is the derivative here? This is 2b's, right? Okay, so this is a 4. All right, so this is a 4 times 32,000. I have 1 over b. What is the 1 over b? The derivative is negative 1 over what? B squared. All right, so negative 1 over b squared. This one will be equal to 0. So then you can say this is the 2b is equal to 4 times 32,000 and b squares, right? I can cancel 2 here, so this is 2 here. Then you do a cross product, right? So you can treat this is 1 and cross product. Then you will get a b cube is equal to 2 times 32,000 is 64,000. So what is the b here? B is 64,000 to the cube roots, right? So what is that? So this will be 40s, right? Right, so the 4 to the cube is 64, right? So it's a 40s here. So it's if this is the 40, so the base here is a 40, 40 because it's a square. Now h, what is the height? Height is 32,000 divided by 40 to the square. So what is here? So this will be 20s here, right? So we know the dimension of the boxes here. So dimensions here will be what is 40 by 40 and by 20, right? So this since here is 20. So the height of this box is 20 here. Okay, so this one's here is is kind of the similar, but as you can see, the objective function getting a little bit more complicated than our level 1 problems here. Okay, let's take a look. The other one, this one here is kind of like backward, like what we did before, right? The previous example. So let's say that I have a 1,200 centimeter cube of materials available to make a box, and with a square base and open top. Okay, so this is the box again. Let's draw this ones here. We always draw it. It's easy. This is a square box. So the same old. We say this is the B, and this is what this is the height of the H. Okay, so now I want to find the largest volume. All right, so always find the objective function. Okay, so your objective function is the largest volume. So what is the volume? It's the base square times the height. What do you want to do? You want to maximize that, right? Okay, so now what is the conditions we have? So condition here we have, is we total have 1200. This is the square base and the open top, right? So that means my surface area is equal to 1200. And this 1200 is going to be equal to the 4 side. So it's 4 times BH plus what? B squared. All right. Okay. So now this one is just like the backward of the other one. So now we need to try to solve the, okay, so let's try to solve the equations here. So for here, I think that I will still, I want to change this to be a function of one variable to be a function of the other one. So here, I think it would be easier to change the h equal to, because I don't want to take the square roots, right? So you see the 4bh is equal to 1200 minus b squared, correct? And then the h is equal to what? Is 1200 minus b squared over what? Over 4b's here, right? So if you simplify this one a little bit, so this will be 300b, all right? And so what is here? So this is 300b minus 4b, all right? Now you substitute to your objective function, right? This is the variance, right? Okay, so the variance here is b squared times h. H is 300 b minus b over 4. All right. So now here your distributive property. So this will be the b. So this will be, let's say this is 300. Okay, let me erase that. Okay, make sure don't be too messy. So here this is b and the b cancel. So this is 300b minus what? B cubed to the what? To the 4 here, right? Okay, now the next thing here, take the derivatives, right? So the derivative here, this is 300 minus what? 3 over 4 b squared, right? You set equal to 0, and then you solve for b. So you have 300 is equal to 3/4 b to the what? B to the squares, right? So then you will get the b squared is equal to the 400. So what is the b? B is equal to 20, right? Okay, so b is equal to 20. So now you substitute back here. So what is h equal to? H equal to 300 over b. So it's what? Over 20 minus 20 over what? Minus 20 over 4 here. All right. Okay, so now I will find what is my h's here. So this is 2. This is 15 minus 5, right? So 15 minus 5 half. So my h is equal to what? Equal to 10, right? So now I want to find the largest variance. So the max variance is going to be what? B squared times h. So it's 20 squared times what? Times 10, right? So this will be the 4,000 centimeter cube. That will be my maximum volume for this open box here. Okay, so we did the problem 3 and 4. So these two problems, are very similar, like a level 1 optimization problem. It's just our objective functions and our condition become a little bit more complicated. All right, that's it. That's it for the optimization problem level 2 practice, and looking forward to see you at our level 3 practice. Let's see how complicated the optimization problem can become too. All right, nice talk to you, and looking forward to talk to you again in our next videos here. Okay, bye-bye.